When you first power up an ATV320, the Simply Start menu is ready for basic tasks. If you just need to spin an exhaust fan and set a simple acceleration time, those top-level settings work within minutes. However, industrial reality rarely involves unmonitored movement. Applying that logic to a high-tension conveyor or a heavy crane often leads to a catastrophic failure. To solve these physical engineering problems, we have to move past the Simply Start menu. We need to access the drive's full configuration architecture. The exact map for this territory is the ATV320 Programming Manual. This document provides the specific codes needed to translate machine requirements into physical movement. Navigating complex parameters is faster if you upgrade your hardware. Using a graphic display terminal gives you clear, multi-line access to the full menu paths. Utilizing the full configuration architecture establishes the ATV320 as the primary logic center for the entire machine's operation. Consider a common factory scenario, a packaging conveyor belt. The operator needs a physical analog dial to adjust the speed, but an independent digital sensor determines exactly when the belt starts and stops. By default, the drive operates in a combined state. It expects the run command and the speed reference to arrive through the exact same channel. To split these signals, we navigate into the command menu, shown on the screen as CTL. Here, we switch the configuration from combined to separate. With that change, the drive can simultaneously process an analog input for its speed reference and a digital input for its run command. Using the command menu this way removes the need to wire external relays or complex routing logic, which simplifies the machine's overall wiring schema. In textile winding, the stakes are higher. If it takes up real spins independently, the thread will quickly pile up in the center and jam the machine. This requires a thread guide motor to move back and forth in perfect synchronization with the speed of the winding reel. We solve this in the Application Functions menu. This section allows us to activate traverse control and synchronization to link two separate ATV320 drives. This system diagram shows the required architecture to establish a master and slave relationship. The master drive on the left controls the thread guide, while sending a synchronization signal directly to the slave drive running the winder motor. These application functions enable independent drives to maintain precise mechanical synchronization, allowing them to operate as a unified network. Operating complex machines on a hot factory floor creates significant thermal risk. Extreme heat is a primary cause of motor failure and hardware damage. The drive's defense lives in the Fault Management menu. Navigating to the PTC section allows you to configure thermal monitoring parameters. This schematic outlines the integration. An engineer wires a thermal probe from the motor into a digital input, such as DI6, which feeds real-time temperature data back to the drive. Configuring these faults enables the drive to monitor thermal thresholds and halt operations before any permanent hardware damage occurs. We have now engineered a robust system with separate control references, synchronized movement between axes, and active thermal protection. The actual capabilities of a modern variable speed drive are defined by its internal software architecture rather than its physical copper and steel components. Mastering the full configuration menu saves cabinet space and reduces costs by eliminating the need for an external PLC to handle standard mechanical logic. Download the ATV320 Programming Manual, document NVE 41295. Map out your specific application and use the configuration menus to increase your machine's intelligence. Subscribe to the channel for more. In our next deep dive, we will explore linking these drives to factory networks using protocols like Modbus and CANopen.